Let's look at simple applications of Newton's law. Let's imagine that we have an object sitting on the ground. The technique in using Newton's second or first law is the following. First, we need to identify our system. That is, we want to be very clear about which system we're going to apply the first or the second law. In this particular case, I have one box sitting on the floor and I am interested in the box. So that's trivial. This will become important when you're going to be dealing with composite system. So when you only have one system, no worries. In this particular case, the box is my system. Second step, you need to identify all the external forces acting on that particular system. Let's go over the typical forces that we're going to see in this class. The first one that should come to you or come to your mind is what we call the weight. The weight is the force due to gravity which is acting on any object which has a particular mass. And remember that we mentioned that force when we're doing kinematics when we replace the acceleration by g. So if you have a particular object whose external force is only the force due to gravity, then the acceleration is g. So this is the same thing. This force is called the weight and is being defined as the mass times the acceleration g, which is 9.8. We know its magnitude, it's always going to be the same. And we also know that its direction is always going to be coming from the top, coming down, in a sense, like this. So always coming from the top, vertically down. That's the first one that should come to mind. Second force is called the normal force. And this force will always be present every time your system, in our case the box, is sitting on another surface. The normal force will be the force coming from that particular surface onto your object. Now in this particular case, let's investigate why we need a normal force. If we go through our list of forces, the first one that comes to mind is the weight. And the weight we know is a force in this direction, always, whose magnitude is mg. Now we know that this is a vector, therefore we can move it, and I'm going to draw it from the center of mass. So this particular force W can be drawn here. Now as I'm doing this and I'm looking at my object, I know that my object is not being accelerated. It's sitting on the floor. And yet I have just identified a force W which should cause, due to Newton's second law, this particular object to be accelerated down. And obviously it's not, so there must be another force keeping it that way. That's the one. The normal force in this particular case is the force from the ground acting on the object. Now in this particular case, the normal force has to be exactly equal in magnitude as the weight, but in general it doesn't have to be. So do not remember this as a property of the normal force. Instead, what you should remember from the normal force is that its direction is always perpendicular to the surface into which your system is lying on. In this particular case, my surface is horizontal, therefore my normal force is perpendicular to it. That's all I know about my normal force in general. This is all you should assume. You should never assume that the magnitude of your normal force is equal to the weight, because 99% of the time it will not. The only thing you can assume about the normal force is that its direction is perpendicular to the surface into which your system is sitting on. Okay, so first force weight, second force normal. Then the third force that you should identify is any force that's being applied to your system, and usually that's what the problem is telling you. The problem might tell you, okay, there is a system and I'm pushing on this system with a particular force F, like this, or I'm pulling with a particular tension, T. They can give it any name they want, T, F, G, P, R. It can be pushing, pulling, whatever you want. So usually those forces are given to you in the problem. That's what you're going to put. Now again, remember those forces are vectors. So to help you go through the later steps, I would always suggest always draw your forces from, let's say, an imaginary point which is somewhere in the middle of your object, which we'll call later center of mass, which will make your life much easier as you go through the later step. So this particular force F, which is a force which could be a pushing force, somebody is pushing on that object. Take that force, since it's a vector, move it and plot it from the same point at which you plotted W and N. Similarly, T, if you're putting on your system T, take that vector and replot it from your center of mass. Okay, so let's do that carefully. Oh, nice. Okay, so take the habit of taking your forces and replotting them starting from the same point. Whenever you're going to be doing translation, you can always do this safely. Whenever you're going to be doing rotation, we won't have that luxury. But as soon as you're doing translation, take that habit. It will make your life easier. Okay, another force that will come later on is called friction. I will not go into detail about the functional form of this force just yet. I just want to mention one of its properties. The frictional force, again, same as normal force, we will never know its magnitude off the bat. But there is another property that we can always figure out, and this is the same as normal force, it's its direction. We know that the direction of the friction is always going to be opposite to the direction of motion. That is, in this particular case, if I'm pushing this object with the force T and the force F, most likely this object will go towards the right, somewhere towards the right. If there is friction, which is coming from the surface, if the tendency of the object is to go towards the right, then the friction is always going to try to go opposite, to go against the direction of motion. Therefore, in this case, the frictional force will be going left. So the property of the direction of the frictional force is that it will always be against the direction of motion. Most of the time, the direction of motion would be along the surface into which the system is sitting on. Therefore, the frictional force will most likely be parallel to that surface. So that's what we call surface friction. We will see some other types of frictional force later on. So again, frictional force magnitude, never assume anything. Direction, always try to figure out what is the tendency of my object, or what is the direction that my object has tendency to go towards to. Whoa, that wasn't too good. Try to figure out the tendency of the object. Try to figure out in which direction that object tends to go. There you go. I'm sorry. So try to figure out the tendency. Try to figure out in which direction your object tends to go, and then pick the other direction. Bang, done. Okay, let's move on because I'm not doing too good. That's it. That's it. So that was the second step. Third step. Choose a coordinate system. In this course, we'll be dealing in 1 or 2 dimensions. Now, how are you going to pick a coordinate system? You're free to pick anything you want. There's 2 suggestions in choosing a coordinate system. First one, you want to pick a coordinate system such that the most amount of forces are aligned along your axis. So remember, you can pick any coordinate system you want. Usually in this class, and to make our life easy, we will always choose an orthonormal coordinate system, which means that the x is perpendicular to the y, and the unit vector in the x is the same as the unit vector in the y. Sorry. So we know we're going to pick something like this. But you could pick this, or you could pick this, or you could pick this. Anything you want. So you want to pick one such that the most amount of forces are directly aligned along your axis. In this particular case, the most natural one to pick would be one who's aligned along two forces, N and W, up, and the other one, let's say, along the F, because you want the other one to be perpendicular. So that covered 3 forces out of 5. That's pretty good. And then you pick. You can choose this y to be positive up, and then either x positive towards the left or x positive towards the right. Doesn't matter. You decide. Okay? The other suggestion is that if you know, or if you're being told that the system is being accelerated and you're able to figure out the direction of that acceleration, always pick one of your 2 axes along that direction. So let's say if you're being told that the acceleration of this object is going towards the right, then definitely you want to pick one of those 2 axes in the same direction. If you were being told that A is going that way, then you want to pick a coordinate system along the direction of the acceleration. You don't have to, but when you're going to be doing circular motion, it will simplify your algebra greatly. So I would suggest you do that. Okay, so that was this. Which step was that? Third. Last step, apply Newton's second law. Now remember, this is a vector equation. So you know that you are going to apply this equation to this system. So you know that this m must be the mass of your block. And you have figured out all the external forces, therefore you know the left hand side entirely. Then you can go ahead and figure out the right hand side. So the same way as we added several vectors easily, we can add several forces easily. We have 1, 2, 3, 4, 5 forces in my case. Therefore, I would have to add F plus T plus N plus, what do I have, W, and then I had little f. So I have to add all those forces. Now I know that whenever I want to add vectors, the best way to do it is to write my vector into component notation. That's the reason why I picked the coordinate system. So all I have to do is break down this vector equation into 2 scalar equations. One in the x direction and one in the y direction. That's my x and that's my y. Therefore, I need to calculate fx, wx, nx, tx, fx, fy. Whoops, that must have been a ty, ny, wy, fy. That is, I need the x component of my n force, its y component, the f, the x and y component of f, the x and y component of w, etc., etc., etc. Which means that for me to be able to figure out every component, I need the angle between each force and either my x or my y-axis. Otherwise, I will never be able to get the x component. So remember, you can always decompose any vector, let's take the case of t, into 2 components, tx and ty. F can be decomposed into 2 vectors, fx, fy. W is already along y, therefore it doesn't have any x component. That's nice. Similarly, f is already along the x, therefore fy is 0. And similarly, n is already along the y, therefore nx is 0. So really, the two forces that will give me some work are t and f. So for me to be able to calculate tx and ty, or fx and fy, I need either the angle between t and x or the angle between t and y. Similarly, I either need the angle between f and x or the one between f and y. So I have to figure out those angles, or they have to be given to me. Let's imagine they're given to me. This is alpha and this is beta. So I know the angle between t and x, and I know the angle between f and y. So for me to be able to fill those two equations, I will need the following: fx, fy, nx, ny, tx, ty, fx, fy, wx, wy. Let's start with fx. F is already aligned with my x-axis, therefore the full vector is along x, therefore fx is nothing else than f. But f is pointing towards the left, and I decided to have positive x towards the right. Therefore, due to my own decision and my choice of the coordinate system, this must have a negative sign. Similarly, fy, since f is directly aligned along x, it doesn't have any y component, fy is 0. Done. Nx, n is directly aligned along y, therefore if you take the x component of n, you're going to take cosine of 90, which will give you 0, and x is 0. And similarly, ny is n. Now n is pointing up. I decided to my y positive going up, therefore n is positive. Looking good. Let's skip the hard ones. Wx. W is pointing down, it doesn't have any x component, bang, 0. And it's directly along the y, therefore the full vector is along y, therefore this is fully w. And w is pointing down, I decided to choose all my vector going up to be positive, therefore negative w. Okay, now let's look at this. We see a nice little triangle T, Tx, Ty, alpha. Therefore, no problem. We know that Tx is T cosine alpha, and Ty is T sine alpha. Tx is going towards the right, Ty is going up. They're both positive. Good. What about f? F is, so this is my x, this is my y. F is going down, and I know this angle beta. So I can decompose my vector f into two vectors, fy, which is going down, and fx, going right. So we have a nice little triangle here. Fx in this case will be f sine beta. My fx is going towards the right, therefore it's positive, and fy is the adjacent in this case, therefore f cosine beta. And this one is going down, therefore negative. Okay, that's the idea. So now all we have to do is plug all the x into my equation, add all the x together, add all the y together, bang. So let's do that. Fx is minus f, tx plus t cosine alpha, nx 0, wx 0, fx again. Oh wait, I picked the wrong fx. This one was here. This one f sine beta. Excuse me. Okay? And this must be equal to m ax. So if I'm given the magnitude of f, I'm given beta, I'm given the magnitude of all those forces, all the angles. Now I can figure out the acceleration in the x direction. What I need to do is add all those guys divided by m, done. Similarly, I can figure out the acceleration in the y direction. What I need to do is add all the y component, fy minus f cosine beta. Ty is going to be plus t sine alpha, ny plus n, wy minus w, fy 0. This is may. Done. Now in this particular problem, if I'm being told that my object is actually moving along my x direction, so along the surface, then we know that this object is not jumping up and down in the y direction. Therefore, from a physical constraint, we know that this is equal to 0. So we could use that in case we were not given one of them. Okay, so let's take another example. If we have, so let's take the same case but simplified. What are the forces acting on this system? System being my block. Weight, normal force. Therefore, I can pick a current system y, x. Let's do the sum of the forces is equal to ma. Let's do it in the y direction. I'm going to end up with n minus w is equal to 0. Given that my system is just sitting on that surface without being accelerated. Therefore, I know that this is equal to 0. In this case, n is equal to w is equal to mg. So my normal force in this particular case is equal to mg. There is no forces in the x direction, therefore 0 is equal to 0. Now let's imagine that my block is sitting on the surface, but this time the surface is inclined, let's say by an angle alpha. Let's do the same thing. This is my object and my system S. The first force is my weight, down. Second force, normal force. Normal force is always perpendicular to my surface. Therefore, n is perpendicular to this, right here. Is there any other force? Let's imagine there isn't any. So we know from a physical point of view that most likely, if there is no friction, the object is going to slide down. So it's going to move somewhere in this direction. If the tendency of that system is to be accelerated in this direction, I want to pick this as my coordinate system. So I'm going to decide to choose this as my x to make my life easy, and therefore perpendicular should be my y. Okay, so now I'm ready. Almost. I know that my n is along my y, so I would have no problem projecting the x and y direction. But I need to do this with my w too. So I need either this angle or this angle. But I know this angle. So let's summarize most of the possibility that you will see. If you have two lines intersecting, this angle is the same as this angle. If you have this angle is the same as this angle, is the same as this angle. If you have this, whoops, that wasn't too good. Such that this is perpendicular to this, and the other are perpendicular to each other. And this angle is the same as this angle. Now look, we have W here, we have X here, we have y here, and this is our alpha. So start with the alpha. Alpha has two branches. One is the horizontal, which happens to be perpendicular to UW, and the other one, just look for one that's perpendicular to that one. Obviously it's n, and n is along y, therefore it must be that one. So this y is perpendicular to that one, and this one is perpendicular to that one, therefore this is alpha. Let me redo it. Bigger picture. This is x, this is y, this is w, this is alpha. This one is perpendicular to this, and now let's look for whoever is perpendicular to the other one. Bing. This one. Bing. Therefore this angle is the same as this angle, therefore this is alpha. So if this is alpha, then now we're ready to project both of our forces. Sum of the forces in the x direction is equal to MAX. In this case NX is 0 because NX is along the y, and W can be decomposed as this vector WY and this vector WX. WX will be opposite to my angle, therefore it would be MG, which is W sin alpha. WX is pointing in this direction, same as X, positive, and this will be MAX. Similarly, I can do it in the Y. Sum of the forces is equal to MAY. In this case, N minus MG cosine alpha, because this is the adjacent, which is the cosine. It's going down, opposite to my Y, therefore negative sign. N is already a line Y, therefore positive N. Now I know that my system is sliding down, therefore it's not being accelerated in the Y direction. This is equal to 0. So I have two equations. I can use the first one to deduce the acceleration, and I could use the second one for good luck to figure out my normal force. So in this case, you see very clearly that the normal force is not equal to the weight, but is equal to the weight times cosine of the angle. It's only in this particular case where the normal force is equal to the weight.